Now see here, electric field lines for the pair of one positive charge and negative charge having equal magnitude but opposite sign. So see here, the electric field lines are starting from the positive and terminating at negative. So this is here depicted like this, and here coming inward here for the negative. If you have taken two positive charges equal in magnitude, then electric field lines are drawn in this way, and this point is actually here the midpoint is where electric field intensity is 0. So now see here some properties of electric field lines. Electric field lines actually originate from the positive and terminate at the negative charge, and these lines are continuous curve, but they are not close continuous curve. They are forming here the continuous curve here, there is no break in that, and two electric field lines do not intersect each other. So if the two electric field lines are intersecting, like one is like this and one is like this intersecting each other, then at a point there will be two directions of electric field, which is not possible. So two electric field lines do not intersect each other. And also see here, the relative closeness of the electric field lines tells the relative strength of the electric field. So suppose the electric field lines are much more closer at any point, it means electric field is stronger. So these are the some properties of electric field lines. Now see here, dependence of electric field on the distance. Now see here, there is a point charge q, and we have taken electric field lines are this radially outward here. So see here, electric field lines are actually drawn in the 3-dimensional space, or that is in a space. So actually they have got the 3-dimensional nature here, but when we draw this diagram on the plane of the paper, that is in 2 dimension. So we consider actually electric field lines per unit area crossing through the area given here. So actually here we consider here electric field lines density. So electric field lines per unit area is actually known as electric field intensity. So here we have taken to a small perpendicular area, this one is suppose delta S1, and here we have taken delta S2. Its distance from the center is OP1, radius is R1, and this distance OP2 is, that is R2 here. From these two areas, number of field lines are passing equal, that means equal number of field lines are passing through this. In the 3 dimension, we know that we take here the solid angle. So we can write here the solid angle here, that is this omega is equal to, we can write here delta S upon R square. So from here we can write delta S1 is equal to, that is in this area, is equal to R1 square into solid angle, and similarly we can write this S2 is equal to here R2 square into omega. Let the number of field lines passing through these area be same, and that is equal to n. So then the number of field lines passing per unit area is equal to actually electric field intensity. So number of the field lines passing through per unit area, that is equal to electric field intensity, we can write E1 is equal to n upon, we can write here R1 square omega, and for this we can write E2 is equal to n upon R2 square omega, where n is the number of field lines passing through these areas. So we can take this ratio E1 upon E2 is equal to, we will be getting here R2 upon R1, R2 square upon R1 square. That we can write here E is inversely proportional to R square. So as the R increases, so the density of electric field lines decreases, that means magnitude of the electric field intensity decreases.